Hi, welcome to our last part of our mini-series on agriculture. Today we'll be discussing soil carbon. The objectives of today's talk include to define what soil carbon is, understand the importance of soil carbon and its role in the Australian agricultural industry. We're going to have a look at two case studies. One is mine sites and the other rangelands in Australia, and have an understanding of how soil carbon influences both those two case studies. We're going to have a look at the soil profile level and the biological interactions for soil carbon there. And lastly, we're going to have a quick discussion on how soil carbon levels will be influenced by global warming and climate change. So the overview of today's presentation includes an introduction. We've got our two case studies. We're looking at soil respiration, which is the biological scale, and we'll have some concluding remarks. So firstly, we're going to have a look at what soil carbon actually is. So soil carbon is highly diverse. It is basically a species of carbon that is kept below ground. So carbon can be in the form of CO2, which is shown in this diagram here, which is mostly common in the atmosphere. And carbon is influenced by both plant activity or photosynthesis, animal activity through both animals interacting on the land, but also their activities or their biological functions, and also human activity, so development and farming, and also controlled burning with fire. Soil carbon is also highly influenced by below ground activities, because that's where it's stored and kept. So you've got microbial activity, you've got the nutrient cycling, you've got the soil type. So all these interactions and even geology can influence soil carbon levels and its formation. So the factors are anthropogenic, which is human-based disturbance. There's above ground biomass, so you've got trees can store a greater amount of soil carbon or carbon in their soils than shallow-rooted crops. Yet most of Australia is dominated by agriculture, which is shown in this diagram, has these crops that only have their roots going so deep in the soil, compared to trees that have a much more extensive system. Climate influences soil carbon. So you've got rainfall, as well as droughts or floods. And then the below ground or soil related factors, which is to do with the other types of nutrients and the type of microbes that are found there. What's living below the soil and how are they influencing the level of carbon found? So soil carbon itself is really dense. It's made of organic matter, which is like broken down leaves or decomposing organic stuff. So anything that was living can be found in that soil carbon. So our first case study is the benefits of organic carbon in surface mine rehabilitation. So this is important, especially for Australia, because we've got many mines, deep holes throughout Australia. Some of them need to be closed up because they're at the end of their life cycle. So when we rehabilitate a mine, it's vital that we replace and replenish that carbon back into the soil for then future uses to occur. So when we rehabilitate our mine, we have three benefits of adding the carbon back. So they can be biological, physical and chemical. So biological benefits include plant growth. The more plants we have, the more habitat there is, the more cycling in the atmosphere, the more evapotranspiration. Like, plants just do so much. So it's really important that we have healthy soil with carbon so that we can grow these plants. As well as plants, that also encourages below ground fungi and microbes, and they add health and benefits to the soil, so that when this mine site is used for something else, the soil is ready and healthy to go. Physical benefits are aggregation and degradation mitigation. So that basically means at a soil level, carbon allows the soil particles to stick together better, to stabilise, and therefore there's less erosion. It's less likely to erode and it's just a bit healthier. The chemical benefits include pH, electrical conductivity, and pollutant reduction. So this basically means when we add carbon back to the soil, the pH stabilises to a really good level of between 5 and 7, which is great for plants to grow. The salt levels are maintained, because we've also got these plants growing here from the carbon. And pollutant reduction. So when carbon is found in the soil, all those heavy metals and all those toxins that were used in that mine site are then trapped in the soil. So in summary of that case study, soil carbon plays an important role both at the local soil scale, chemically, biologically, but also on a larger scale. So when we have that healthy soil, that can then lead to large economic benefit in the agricultural industry. Our next case study is soil carbon sequestration, and that is specifically looking at Queensland and the rangelands there. Now, rangelands are highly diverse areas. If you look at this map here, we can see that rangelands cover a large section of Australia, and yet there are so many types. There's 10 different types of rangelands, and that just depends on their tree type, their soil type. There's a lot of different factors. So in Australia, and Queensland specifically, rangelands are dominated by livestock production. So there's discussion of whether we can use some of this large land area and share it with the cows and to rehabilitate with trees. So can we grow all these trees on this area, and then these trees could absorb and store soil carbon in the soil, and therefore maybe they can help mitigate our climate change. That would be great. So here we go, we've got our problem. We've got greenhouse gas emissions are increasing. We all know this, it's around the world, they're increasing every year. It's a bit of a problem. The solution, let's store this CO2, this carbon dioxide, into the ground. Let's use this large land mass and store it there. But there are many factors. So if we look at Queensland itself, there's a huge land area, and that is subjected to grazing, fire, human activity, which then also affects how much carbon can stay in the soil. So we've also got climate change. So Queensland's climate's very diverse. Along the coast is completely different to inland. So where's the best area to rehabilitate and to put these trees? And then obviously rainfall is a big factor. If we don't have enough rainfall, then these trees that we're growing are not going to stabilise and are not going to be that effective. So soil types is also a problem. A lot of the Queensland rangelands are clay and carbon don't really mix. They don't enjoy staying together, so if you add carbon to that soil, the clay doesn't stick it properly. There's some chemical interactions going on that it doesn't like. So revegetation could be a problem, because if we grow these trees and they store carbon, what happens if there's a fire, or if farmers don't want to separate their land from livestock and the trees get taken out? All that trapped CO2 is then going to be released into the atmosphere again, and we're back to square one with probably even more carbon dioxide in the atmosphere than when we started. And we also have to look at how we're going to measure it. We need a pilot study. No one's really studied this very well in Australia, so what are we going to do about it? and nitrogen? Do we need to consider other elements, or are we just looking at carbon? So the answer to our problem: rangelands are not reliable to sequester carbon currently. They're very diverse, very complex. We need to increase moisture, so we need to have secure rainfall for these trees. We also need to make sure they're not disturbed, so we need to limit the amount of grazing, which is a little bit challenging in an area that is dominated by livestock. So in summary of that case study, rangelands are highly complex, but they're also really important for Australia's economic growth with all that livestock. But also, if we want to maintain high economic profit with grazing and agriculture, we need good soils, and carbon is essential for that. So soil carbon levels are affected by both natural and man-made disturbances, and we need to study it scientifically a little bit better to understand more. So now we're going to go to the more biological aspects of carbon. We're looking at soil respiration. So soil respiration, or RS, we're going to use in this presentation, is the loss of carbon dioxide from the soil to the atmosphere. So that shows by this arrow coming out of the soil into the atmosphere, or into the cloud there. So there's discussion that there's significant flux of CO2 because of soil respiration. So all these activities, all these biological activities happening under the ground are causing CO2 to leave into the atmosphere, which is not that great because CO2 in the atmosphere, as we know, is greenhouse gas, and that contributes to global warming. So there are many factors that influence soil respiration. As you can see from this diagram, you've just got a couple here. We've got water, temperature, carbon dioxide, plant growth, energy, transpiration, metabolic activity, photosynthesis. And this is all very good in a diagram, but in real world, in Australia for example, this would vary from northern states to southern states, from coastal areas to inland areas. Climate is a huge influence, so weather, how much rain are they getting, how often do droughts occur, all this, as in temperatures right in the middle here, all this affects soil respiration and that CO2 that enters the atmosphere. So impacts of global warming. If we increase carbon dioxide, this then affects, this then allows, I guess, soil respiration to also increase, which then increases CO2 back into the climate. So a positive feedback loop. There's just too much entering the atmosphere and not enough being stored in the ground. So increasing temperature also stimulates root growth and microbial activity and enhances soil respiration. And we know that with global warming, we're going to have increased temperatures. Drier areas will get drier, wetter areas will get wetter. So there's going to be even more CO2 entering the atmosphere. So changing precipitation rates. There will be shifts in weather patterns. There will be changes in extreme weather events. So this then obviously affects microbial activity depending on the area, and then the amount of soil carbon in both the dry areas and the wet areas of the world. So, as we've discussed, the way in which terrestrial ecosystems respond to climate change will vary broadly in both the climatic zones and the vegetation type. Therefore, it's crucial to improve our understanding not only of the controls of soil respiration, but also how they interact and what components interact. And this should be used, this scientific analysis should be used when we implement political policies to mitigate climate change. So, in conclusion, soil carbon is complex and dynamic. There are many influencing factors, we've discussed a lot today, but the main ones include human disturbances such as grazing and fire, direct profile disturbances with mine sites, and then the overarching discussion of climate change and this global warming implications. So I just want to say thank you for listening to this series. If you have any questions, feel free to ask them now, or you can leave a comment on the YouTube page. Thank you for your time.